Okay, I'm just going to go ahead and get started. There's still trickling coming in, but I'll get the intros out of the way. So I'm Steve McConey with Osborne Company. So in general, we are the representative of WaterDrop, which is part of this presentation. Our representation encompasses Northern California, Northern Nevada, and Hawaii. We have two presenters today. We have Misha Egoff. Misha is with New Buildings Institute. If you want more information, New Buildings Institute, you can see on the screen their initiative and their objectives. Misha is technical associate with New Buildings Institute. She's part of their innovation team. Misha is an engineer that applies her engineering skills for conduct data analysis, create data visualizations, and complete technical research for NBAI's projects and initiatives. Through her building science expertise, Misha quantifies the energy costs, carbon impacts, and energy efficiency and decarbonization measures in both the residential and commercial sector. Now, there was Noah Gabriel who was going to present, but Misha, who is her manager, his manager, took up the position. Noah couldn't be available. Then that will follow with Albert Rooks. Albert is with Small Planet Supply. He's also the head of WaterDrop, which is their manufacturer of their heat pump water heating systems. Albert started in the late 2009, 2010 with the goal of passive house construction. He established standards in North America. He founded Small Planet in 2010 in Washington. They have a physical warehouse location, an online store, and the company initially imported and distributed passive house components, including the tapes, membranes, mechanical systems. And now they are basically applying that to manufacturing with WaterDrop and their heat pump systems. So I will turn this over to Misha to begin the presentation. Anyone has any questions? What the Q&A and chat are open. You can do that. If you want to ask a question verbally, you can raise your hand. Misha?
Thanks, Steve, for the intro. It's always kind of awkward to have someone read your intro about you while you're right there, but I do appreciate you doing that. And
Sure.
yeah, I'm like Steve said, I'm Misha. I'm with New Buildings Institute. What we do is here, we're a national nonprofit, and we also notably run the Advanced Water Heating Initiative, which some of you might be familiar with. And I'm just giving a quick intro. I know you all want to hear about Albert and the WaterDrop system. But I wanted to just do a little bit of level setting about why we're even talking about central heat pump water heaters, or CHPWH is today. So there's a few reasons. They are energy efficient. They have a high COP, which notably helps utilities. That high COP also helps reduce operating costs, which helps building owners. They have reduced carbon emissions compared to other alternatives. And they also have this really cool load shift capacity, which helps both the grid and building owners. So it really is a win for a lot of different groups, users. And so if they're so great, why doesn't everyone have one? Well, we've done some research at NBI, funded by the Northwest Energy Efficiency Alliance, or NEA, that was focused on understanding the barriers to adoption of these systems, particularly from the viewpoint of the supply chain. And so through a series of interviews and a survey, this graphic shows kind of what floated to the top in terms of things we heard over and over in terms of the barriers. So complexity of installation was at the top. And I think that that's also related to kind of the fourth barrier here, the lack of confidence in the technology to actually deliver hot water. And I know that Albert will talk a little bit about the WaterDrop system, which really helps minimize some of those complexity challenges, especially that we saw in kind of earlier central heat pump water heater designs. So I will note that this study was completed in 2023. And so this is a rapidly changing market, and there's a lot of great new technology options and designs. People are just learning a lot more about how to most effectively utilize these systems. But we are still seeing that there are some challenges to overcome in terms of those complexities, and also notably higher cost than maybe your basic like for like alternative. So I'm going to just share a little bit more about the landscape of buildings that this might apply to shortly, because that's also a barrier. But I want to just emphasize the fact that there's really, I think, one of the biggest barriers is, with that complexity piece, the lack of installer education. That's something we heard a lot over and over. And so, lunch and learns like this are really helpful to get the information out there. And that education piece can then have kind of trickle down issues, right? So like if folks aren't really sure how to properly commission the system, that can cause issues with the COP, with it not performing as expected. We've heard stories about folks that have thought that maybe they could swap out a part that actually is really not a swappable part just because of lack of understanding. So it's all kind of related, and there are all of these challenges, but there is also a big opportunity. So there are a lot of multifamily buildings in the United States, which is a really key, market for these central heat pump water heating systems. This is just pulling a couple of graphics here just to kind of level set. This is primarily from the Residential Energy Consumption Survey, RECS 2020, and then also the US Census Bureau take stock of where things are at in terms of buildings in the United States. And you can see that on the left graphic, the kind of turquoise color is large multifamily buildings, 5+ units, which is typically the type of building we would see as being a good fit for these large central heat pump water heating systems. And if you look at the graphic on the right, you can see that in some cases for like really large buildings, there's 8 million of those in terms of dwelling units in the United States today. So it is a really large market, and there is a lot of potential. So in terms of what this looks like functionally, so there are, this graphic is just showing the existing water heater size for all of those buildings we just saw. So you can see the left 3 bars are kind of your typical unitary residential size water heaters, 1 in every unit, versus central heat pump water heaters, buildings that are served by a central water heater of some kind. And so how this shakes out is you've got the pink is the kind of smaller buildings, and then the turquoise again is those 5+ unit buildings. But if you add them all up, it's actually almost half and half in terms of existing buildings that already have some sort of centralized water heating system, which is a really large, that's kind of the key potential market for this equipment right now. Right now, it is more financially viable for those buildings that already have just like a 40-gallon water heater in every dwelling unit to just do, to stay at that size versus upsizing to central. But there's still, these 16 million units that have this really easy, relatively easy, like for like opportunity. So I also just wanted to call out that there are some regional things to consider. I know many folks on this call are probably calling in from the West Coast, where we don't have to worry quite so much about cold climate zones. But I do think it's worth pointing out that there are quite a lot of existing housing units that are in that scenario. And that kind of goes back to that lack of.
I think we lost Misha. Albert, yeah.
I think we did.
The whole thing freeze?
I didn't do it.
Oh, you didn't do it? Oh,
Yeah.
Have you lost me?
Oh,
okay,
there.
now you're back.
Oh, you're back.
I'm so sorry. Oh my gosh,
Yeah,
I
no
just got a
worries.
message that my connection was unstable. So where did you
Yeah.
lose me?
You were talking about the stock and inventory in the Northeast.
Yeah.
Okay, well, I won't belabor the point since most folks are probably not in that region anyway. But I think you get the point that this is also a key consideration. So I also just wanted to note, looking at that existing stock, the existing fuel type definitely has, going back to that cost barrier, some financial ramifications. So replacing, moving to electric from an existing natural gas system can require electrification. They don't have the electrical capacity perhaps to add these units. And so then the service upgrade can add a significant cost. And so just another thing to keep in mind with all of this, and I know that Albert is going to share some great information about their system that kind of relates to all of this. So I'm not going to take any more of your time, especially with my unstable connection. But if you do want to know more about the work that we do with the Advanced Water Heating Initiative, more fun facts about the current market or about that study that I referenced with the barriers, you can check out the AWHI resources webpage. We also have a working group specifically focused on scaling adoption of central heat pump water heaters as well that you can join. So with that, if you have any questions, feel free to reach out and I will pass it off to you, Albert.
Great. Thank you, Misha. I will start sharing my screen. Let's get that up there and see. Okay, so we should have a picture of water heating world. Okay, so thanks, Steve. Thanks, Misha. My name is Albert Rooks with WaterDrop Systems. And now we're just going to kind of dive into our end of the presentation. So this is just kind of a cover page shot, but I just want to know the lower right-hand two pictures are our skid system, and we'll spend a little less time on that today and more on the droplet functions. So actually, it's more of the entire right-hand 2/3 of that deck. And the left-hand is a new manufacturing facility where we do assembly of the systems here in Tumwater, Washington. And the middle picture has got a nice guy, a nice picture of a friendly face who is a fellow named Ken Eklund who helped us get CO2 water heating here in North America, ours or anybody else's system. That was he was ground zero. So we are WaterDrop Systems, and we have a couple of different delivery. On the left-hand side is our droplet program that we'll dig into a little bit later. On the right-hand side, it's the skids. The skids and the droplets really were a brainchild, not of our company, but really of the Advanced Water Heating Initiative and NBI. And we'll talk about kind of why that is important and how we're de-risking and trying to make systems more simple to install and simpler to operate. The goal for our company is to be the fully supported, fully immersed partner. So we love to start with the building right at design. It helps if we're involved a little bit towards schematic, or if they understand kind of our product mix, and then we can think about, kind of where the water heating equipment goes. Does it go on the roof? Does it go in a mechanical room? And how all those things work. But from that point forward, we really would prefer to be involved in design all the way through kind of maybe schematic design. And then once a project starts maturing, it turns into kind of factory assembled products and skids and droplet ranges. And then we can create a full specification for an entire water heating system rather than just one or two components of it. And then we also support with our partners such as Osborne, kind of bidder installer training and factory startup. And then everything we make comes with a warranty. It's our warranty, so we're the point of service rather than individual factory warranties, which, when you look at a skid system for us, it's 300 items. And, there's a mixing valve and there's an expansion tank, and all of those things in a typical site-built system, you'd be, kind of looking for warranty support from wherever those things came from. In our system, we're here to kind of de-risk and create simple relationships, simple systems. And so we're really kind of want to be the point of contact and kind of support the project. So there's a friendly face again. Ken Eklund was a paid researcher by Washington State University under funding of the Bonneville Power Administration and NEA. And really their mission was how to serve a growing population for water heating without adding more generation, either in fossil fuels or in electrical generation. And so really, the BPA has been running power plants for a kind of number of decades, and they really lean on efficiency to make systems more efficient so we don't have to add generation. We can account for generation through economy. And so the next project for Ken back in the early 2000s was CO2 heat pumps. And CO2, we'll talk about the refrigerant, but it's really an amazing refrigerant. And that is why Ken went off to Japan to talk to all the manufacturers there, because globally, that's really where the CO2 competence is. And he had a number of conversations, and one company said yes. And then we all started down that road and have developed that technology over the last 15 years, I want to say. And he's leaning against another CO2 product. Actually, this one from China didn't work out. It's a two-stage, nice size CO2 equipment. He and I had it at a lab in Redmond and did a number of test instances on it, and we couldn't really get it to perform the way we wanted. So that didn't mature, but it's just kind of the story behind CO2. And these days we know a lot about CO2 and how it relates to water heating. And it is really a really, really good tool for water heating, because CO2 essentially behaves differently than most refrigerants. So when you put CO2, you put it through a compressor cycle, you're going through the basic refrigeration cycle, and you're putting CO2 under a pressure, you're putting it under a lot of pressure. And the pressure, the operating pressure is like 1400 to 1600 PSI. And in that state, it's pushed across its transcritical boundary. And so it doesn't operate like a solid or a liquid, or I'm sorry, a liquid or a gas. It becomes transcritical. And so essentially what that means is it has the density, the energy density of a liquid, yet it's still a vapor, right? So it's kind of gone across this transcritical state. And so we take this, and essentially what we have is this super compressed, high temperature vapor in this high compression. And so all we got to do is just point that at a gas cooler rather than a heat exchanger. In this instance, it's a gas cooler, because we're just going to cool the gas, and we're going to take the output of that cooling and put it on a little pipe of water. So the graphic on the right-hand side is us just compressing that refrigerant all the way up to, kind of past its transcritical, gets a high temperature. It's a really predictable temperature at that point, and vapor compression and kind of conditions. And then we just show it to a gas cooler, and it drops through the gas cooler. And the other side of the gas cooler is a little pipe of water. So the energy, because it's in this highly dense, highly compressed form, and it drops through the gas cooler, the energy just flips right over to the water side. And so really, to make that transaction, we just need three things. We need a compressor. The compressor takes a little bit of electricity and compresses the refrigerant. We need a water pump, because we're going to push the water opposing that high temperature refrigerant in the gas cooler. And we need a variable water pump. So that way we can just kind of feather the velocity through the water side of the gas cooler to maintain a steady leaving water temperature, right? And so we just use a variable speed pump. So that's a little bit of electricity. It's not a very big pump. It's shockingly small. And then we need a fan. And the fan will just, kind of blow air across the back coil. And there we go. We've got our little packaged unit. And so really, in those conditions, we've got a really special circumstance, because the output and the conditions that we operate in, because of these high pressures and CO2, is we can really do that in any North American ambient. Doesn't matter if we're all the way down towards the Mexico border, or all the way up towards the Alaskan border, or midway up the BC province, or somewhere cold in Canada. Is we don't have to have a lot of energy come across the coil and lift the refrigerant temperature up, because that refrigerant's operating in these transcritical conditions, and there's a whole lot of energy there. So we do get a boost, and we get better COPs when we pull some energy in across the coil and then send it through the cycle. And also with CO2, because we have the state that as we compress the refrigerant, takes on all that heat, we dump a lot of heat against the water pipe as it flows through, then we still got some warm refrigerant, and we can expand it further, send it out to the evaporator coil. And with CO2, as we expand it, we can make some really, really cold fin temperatures. So I've got projects, original kind of first research trial projects that we did way up midway in the British Columbia province of Canada, a serious 12-hour drive north of Vancouver, BC. And it's data logged, and we see some regular minus 30 C conditions every year. And the thing just keeps cruising, because in that minus 30, there's still usable energy out in the ambient that we can bring across the coil and send through the system. We still have a steady leaving temperature of 150 degrees Fahrenheit. We don't have a defrost derate, because the way these systems do defrost, or at least our system does defrost, is it's a hot gas bypass. Because we're working with such high pressures, there is no reversing to kind of make the coil hot and burn off the frost. What we do is we take a little bit of that high temperature refrigerant and send it around to the coil, and it burns the frost off, while the rest of the refrigerant is still going into the gas cooler and running the normal transaction, still delivering a steady supply of 150 degree leaving water temperature, right? So there is no defrost derate. There's a little loss of efficiency, and there can be some capacity losses, but they're not anything that we really need to accommodate in a sizing like we would with a 410 unit that really goes through, kind of a reversing and is really affected by capacity loss due to ambient, or capacity loss or due to defrost. So out of that, with CO2, we get these really high COPs, and these are just kind of at the heat pump, right? It's not an annual systemized COP, but these things work really well. So all those transactions kind of continue through the system, but we can get, in 80 degree Fahrenheit, a 5.5, in the 45, which is unfortunately where I spend most of my life, being here in Washington State, something around a 4. And 5 degree, we still have full capacity, 4.5 kilowatts on these 4.5 kilowatt rated units at 2.25 and so forth. And so all of this rolls up to the fact that when we look at a load and we look at a building, we do a load sizing in the eco sizer, and it says, hey, you need 180 kilowatt, 180,000 BTU to operate your heat pump, right? And so we can size to 188 with the standard rating of the equipment. We don't need to upsize the equipment to accommodate a defrost. We don't need to upsize the equipment to accommodate a colder ambient. If we're in a colder ambient, we can just size right to the load. That is unique with CO2. CO2 has got some drawbacks, or not drawbacks, it's got some operational challenges that make it challenging for non-water heating applications. But in water heating, big dump load water heating, like multifamily residential, it is perfect. And there really aren't a lot of complications with it. We'll see one or two and talk about them. Super interesting stuff. But really, as we look at a building, because we're looking at systems, we're not just saying, here's a heat pump of this capacity, go ahead and choose your tanks, choose your pumps, all that kind of stuff. We're kind of in the whole system. Then we'll look at it and say, okay, here's the building. We'll understand what the building use is, which will kind of give us a load profile. Once we understand the load profile, then we can kind of do a sizing. And so these are real buildings in downtown Seattle they used to be electronic, kind of like the nerd electronic store in downtown Seattle in the old days, and now they're residential housing. And so part of their development was full M&V. So we understand the loads, and these loads went in to inform the eco sizer and so forth. So anyway, that's what the building looks like. Big morning load, good size afternoon load or evening load. And so as we approach that building, essentially what we're doing is we're going to go at that peak and cover that peak with storage, not recovery like we would with an electric water heater or boiler or something like that. This is just high temperature water storage. And so once we have that peak covered with storage, our next question is going down the line is how much time, what's the behavior like between now and the end of the first peak and the beginning of the next peak? And that's our recovery period, right? So the sizing software will inform us as to what the duration is, typically, what the next peak amplitude is, and therefore what the useful water load looks like, and then we can start kind of developing our system around that. Essentially what we're looking at is third bullet point down on the left-hand side is the heat capacity is sized to recover peak in a reasonable amount of time. For me, that reasonable amount of time is like 3.5 to 4.5 hours. And that way, I know that in most all circumstances, I can recover that primary storage in 3.5 or 4.5 hours and be ready for another full peak event. In the afternoon, I'm probably not getting another full peak event, and I've got plenty of overnight condition to get ready for that morning peak event. And that's typical of this type of a building. In senior housing, it'll look a little different, a little less amplitude on a morning peak, more activity kind of across the day. Behaviors are all different. In any case, we can understand it. And that third bullet point says 4 to 8 hours because some projects have different goals. And we want to do all that recovery. We're in an area with a lot of solar access. We really want to leverage as much PV, kind of local energy, renewable energy. And so rather than set our recovery times up and our capacities up for, 3.5 to 4.5 hours, some projects will look at it and say, I want a longer period of time. Or I might want to do load shifting and some other things. These are all kind of negotiable points and tunable points. So as we step into the software that we use, we are working with the ecosizer. Typically, there's other ways to size a load, and we're happy with anybody, however they want to size a load. And if they want our input, great. If they don't want our input, that's fine too. Um, and essentially the ecosizer is, maybe 4 to 5 years old now. Yeah, probably about that. It was developed by utility funding by a couple of great engineering groups in Washington State and California. It's currently managed by Ecotope in Seattle. And it's a tool that you can come in. There's been a couple of new features since this slide is developed where you can kind of choose different load profiles, but you can just come in here to a home page. Number of apartments are on the left. Occupancy rate, it's a drop down. I pick one. Peak gallons per day per person. It's a drop down. I pick one. And essentially what's going on is we got a building. Now we establish how many units in the building. We choose an occupancy rate to kind of put people into those units. And then we choose peak gallons per day per person to kind of cover what we think the domestic hot water is that they're going to use. So we got people in a building, and then we've got usage in a building, and then we're ready to kind of take the next step. Water temperature on the right-hand side, we plug in our entering water temperature, out of city mains. And supply is kind of that mix, after the mixing valve, what our service temperature is to the fixtures, and then hot storage. And in our equipment, it's 150. And then we push a button and it'll go forward. It'll give us a whole recommendation. This covers about 3 screens. And so I boiled it down to just this one screen. But on the right-hand side, I've got the inputs that I used. And design cold 50, and that's for water temperature, not ambient. And supply is 120, and storage is 150. And I've got all those units with a total occupancy of 90. And I think I selected kind of like ASHRAE market rate, which is a really safe, dependable usage, unless we see federal policy saying, well, we don't need shower heads anymore. We just need a 3/4 inch pipe coming out of the wall, in which case we're using a little more water at that fixture. But currently, kind of with the plumbing codes the way they are, we've got we've got kind of all those fixture rates covered. And what'll happen is, remember, the first thing that we want to do is establish the tank volume, because that's how we're going to serve the load. And then on the right-hand side, now we're going to recover the load. So we need heating capacity, right? So in this building, recommendation is 430. So me, because I know tanks and make choices around that, I know I've got a 450 gallon tank. So I'd be kind of looking at that to cover that supply, that storage volume. And then I've got a heating capacity of 97. I've got systems that'll cover 97. Swing tank volume, that's a number. It's a small number, and mindful that the swing tank carries all of the building water through it, all of the building domestic hot water through it. So if we got a little 50-gallon tank and that's what we're going to use, we got to make sure that it's got necks and nipples that'll support the total flow through that little swing tank. And then resistance element, we'll talk about why. And then there's Title 24, which has got a slightly larger swing tank, and we can kind of talk about why. But here's how it all works. And then after this, I'll show you, we turn this into a system. But this is kind of our central point. And this is a design based on single pass. And single pass means that we take entering city water main, lift it up to our storage temperature in one pass. And CO2 is really, really, really good at that, like really good at it. And that's how we get those really high COPs. And that means that we have really a very low connected load of the plant to the building, because we don't need a lot of electricity to run all these little compressors and fans and pumps and things. So we start in the center, primary storage. It's got a blue splash of water on the bottom. That's a stratified tank. So over on the right-hand side, lower right-hand, we got cold city water entering. On the left-hand side, it hangs out there a little bit as a cold stratified layer. And then it exits the tank on the left-hand side and goes into the cold water supply main, or supply manifold, sorry, for the array of heat pumps, right? It could be one heat pump, could be a lot of heat pumps. And essentially those manifold into the heat pump. There's a couple of special things about the way they manifold and the way they operate and stuff, but essentially those heat pumps will do a single lift from 50 to 150. It's always a fixed leaving water temperature, no matter the ambient, no matter the condition. It's always 150. It's not any different. So out of that heat pump array, each heat pump throws a steady rate of roughly 20 gallons per hour of 150-degree leaving potable water temperature, and it all goes into the manifold heading towards the top of the tank on the left-hand side. So we push it into the tank on the left-hand side. Notice this tank has 4 ports. So push hot water into the tank and it stores. And if we just imagine there's no building, and we start with a cold tank where the blue layer is all the way at the top, and we just run, we take cold water out of the bottom of the tank, we lift it, and we push it into the top of the tank. We just run that circle for a while. And pretty soon we'll have heated the entire tank, and we'll push that cold water stratification layer out of the way. It'll disappear. And when we see that high temperature water kind of going out of that cold supply manifold lower left, we'll know the whole tank system is full, and we can tell the heat pumps to stop operating. Okay, so that's just our generation cycle. That's our storage, and that primary storage in the middle is how we're going to serve our load. So, so then we pull hot water. Now we're going to add a building. We'll pull hot water out of the top of the tank, and then give it over to the swing tank, so it'll travel over, and we're giving it to a swing tank, and the swing tank's an extra little tank. And the reason that swing tank is because we'll back up and we'll just take one look at the way these CO2 heat pumps operate. They only ask for kind of one thing in life. And that one thing is always, always, always give me cold water. Because you remember kind of how this works is we get cold water, we do a 100-degree lift, we got this highly compressed refrigerant that's a vapor, but it's the density of a liquid, and it's got all this energy, and we're going to throw that energy into the gas cooler. Well, so that's always happening. And if we and that gas cooler is giving the energy to the little pipe of water. If the little pipe of water starts at 50, we can absorb a lot of energy out of that gas cooler. If it starts at 80, that's less energy, because remember, our leaving water temperature is always 150. So as the incoming water stream increases in temperature, we lose the delta T that we can place the energy. And at some point, we can't slow down the compressor enough. We can't push the little pipe of water fast enough. And that means that the energy is left in the gas cooler, and the system won't like that. And it'll just say, nope, I'm done. So these systems always really want cold water. They'll take a lot of variance. This is not a risk in operation, but in order to get them operating smoothly with the highest COP, we always give them cold water. So the way that we can give them cold water and keep that blue splash of water at the bottom of the primary storage tank is to not hook up a recirc return into the primary storage. So we take that swing tank, we park it off to the right, and we take water out of primary storage at a full 150 degree. We flood that swing tank. And then when there's a load, it comes out of the swing tank at 150, goes across the mixing valve, mixes down to our service temperature, 120, 125, something like that, out to the building, and it's available for use. Some gets used, and then there's always a recirc return coming back. If we brought that return back to the primary storage, we start mixing that tank, right? Because we've got 150 degree full temperature water coming from the left and 110 degree water trying to come in from the right. We lose that stratified layer. Once we lose the stratified layer, we got warm water at the bottom heading to the heat pumps. Heat pumps can't place their energy. And so the system is not happy. If we place that recirc return into the swing tank, then that's a little loop, right? That's completely independent. And really the only issue with the swing tank concept is it's a small volume tank. In our building, it could be as little as 50 gallons, and that 50 gallons had access to 7.5 kilowatts of electric resistance in it, because what'll happen is it's all fine when there's a load and the load exceeds the recirc return. And so, if the load's 6 gallons and recirc return is 3 GPM, right? Then we've got more load going to the building. We've always pulling 150 degree water out of storage. And then when storage starts getting depleted, we regenerate using the heat pumps. So when people go to bed and they're not using anything, now we've got a kind of a closed recirc and there's not really a lot of load being used. So we're taking 150 out of the swing tank, mixing it down to 100, 120, sending out to the building, bringing it back to 110. And sooner or later, we're just going to cool that tank because we're just going to give the energy to the distribution loop in the building. So when that happens, then the electric water heater says, aha, you're starting to get cool. I'm going to reheat you back up to my set point. And that set point needs to be a little above what my entering water temperature is on the mixing valve so that I'm able to, so the mixing valve isn't hunting all the time, right? So we've got to give it a decent approach. So that's how these systems work. They're simple, but they're complex. They work really well when they're set up and operating this way, extremely reliable. So the main thing is to just get it designed, installed, and operating correctly. And that's really what we do. So now we're going to start looking at how we actually deliver those designs. And there's a few simple ways. One way is a skid. And that concept is to completely de-risk and make everything simple. And we build the entire water heating plant, and it shows up to the building on the back of a truck, and it shows up with skins, kind of like the nice blue pictures in the front. And you literally lift it off the truck, place it where you're going to place it, hook up 3 water pipes, 1 power landing, and yeah, that's it. 1 power landing, turn it on, flood it, burp it, and let it go, and it is your water heater. So it can be typically installed in a day, started up the next day, and so 48 hours, there's a full plant capable of serving, 30 people to 160 or 180 people. Then there's another delivery system, because not all buildings are set up to receive a big skid, 1 or 2 skids on top on a roof or a grade or wherever we're putting at it. And many buildings are designed with a mechanical room. So in a building like this, new construction in Seattle, it's up and running. We can see this one on the cloud. Lower right-hand corner is a thing we call a droplet. So that's the CO2 heat pump plant with all the controls and a single power landing in that gray box kind of on the left-hand side of the picture. And those are all running, and we stage those. They don't all come on at the same time. There's a whole set of controls and operating principles behind that. And on the left-hand side is the mechanical room. Two white spray foam tanks in the back. That's primary storage, no elements in it. And so really our droplets are heating those tanks. And once those tanks are fully heated, then the droplets can turn off and wait patiently until the next load. And then you can see there's two electric water heaters there. So normally you only need one, and it would be much, much smaller. But we're in a transition period, right? And so, and that's fair. So this is a method that someone used to de-risk the fact that maybe heat pumps are new and I don't quite trust them yet. And so how am I going to build in redundancy? So this is a good time to talk about redundancy. So those electric water heaters are sized to pick up part of the load or all of the load. I'm not sure of the sizing, but they're, they're looking pretty good. And so they can be there. And if they never receive cold water, they never turn on, right? So it's kind of a bit of a capital expense to kind of get that redundancy built in there. And they do have to kind of do that recovery as we give the energy out of those swing tanks over to the distribution loop because we're just running recirc and nobody's really taking a load. Then we have to we have to lift that tank volume. So it's a big volume, so we'll wind up having to lift that. But it's not an unreasonable approach to do that. The right-hand side is our approach to redundancy. Like if I had one heat pump and I'm living off of one pump, one control board, one of everything, then having two big electric water heaters kind of makes sense to me. But on my side, the reason we do what we do the way we do it is those are 12 heat pumps. I've never ever had 12 heat pumps go down at once unless there was a power outage, right? If there's garbage in the water and maybe a water pump struggles or somebody hits it or there's a little vandalism or something like that, then sure, one heat pump could go down. And what's the effect of that? Or even two heat pumps go down in this rack of 12. Well, if we go back to that original kind of sizing story, we're serving the load with storage. And then we're using the heat pumps to recover storage after we've given the storage to the load. So what happens if one or two of these heat pumps go down? It doesn't affect the load or the building and the occupant. It just means that it takes a little bit longer to recover the storage. Give it time. Those, I don't know what percentage 2 is. Oh, well, 2/12. 2/12 missing capacity is just means that it's going to take a little bit longer to recover the storage. It does not indicate that we cannot recover storage even in a reasonable amount of time because we've got room kind of in the sizing. So we've got built-in redundancy, and the way that these things are piped and designed, we can even take one intentionally out of service or two or three out of service and work on them, replace them, or change programming or anything like that, and everything keeps going. And so really the way we do this is we build these racks called droplets. They have full controls. They are capable of doing load shift. They are all cloud connected, so our engineering team can see them at all times. And we pair them with tanks. Our tanks, you can notice, have 4 thermistors because we're going to do some load shifting later. And so now we got heat pumps and tanks, and that comprises the major components of the system. And we're ready to go. So back of the system looks like that. It can go in any climate. It's preheat traced for northern climates, and it's all insulated, 100% ready to go. The red steel pallet there is really the transport pallet. So on installation, the system unbolts from that pallet. You just set it in position, screw it down to wood or concrete, and connect your 2 water pipes. Give it power into that single panel on the right, and it's got LTE signal, built-in SIM card, and as soon as it powers up, we can see it on our engineering desk. And we can look at it and say that's about 185 kBTU of capacity, but they'll chain together. So we serve big loads by just chaining together multiple droplets, and we make droplets from 2 heat pumps all the way out to 12 currently. And so we can join any number of them together. They're all kind of pre-programmed to recognize, a parent recognizes a child and another child when they're introduced. They get programmed as they leave our factory. And so in this case, we got 36 compressors, 4 stages, at 130 MBH each stage for a total of 554 MBH. And that's a good size heating capacity. It'll do a lot of domestic hot water. And then we just pair that with storage to match. We've got a lot of tank sizes. We've got 3 other sizes larger than 500 that we work with. They're all set up to work with 4 thermistor probes. And that works whether there's one tank or multiple tanks. We'll look at that in a minute. And then we get to placement. So typically in these we use these Senko 2 heat pumps, and kind of we gang them together, put them on a rack. Natively, the Senko 2 heat pumps really need to be within 66 feet of their storage, right? So it kind of limits you, kind of like you can put the heat pumps here and the storage has got to be within 60 feet. In our system, we have designed a couple of options where we can put the heat pumps up on roof on level 6 and the tanks at grade in the mechanical room. And we've got controls and pumps that'll operate between the two. It's all within our sphere and it's all supported by us. So we have a number of different options, including kind of high pressure options with bracelet heat exchangers. But essentially we've got mechanical room controllers that'll connect onto the droplet control by a single Ethernet. They'll operate a pump. They'll serve the tanks with the thermistors and some other connections. And so we manage all of those relationships kind of native within our droplet system. And we make just a whole lot of version. These are all versions of droplets in parent and child and in tall heights and in short heights and parkade heights that are designed to fit under a 7-foot concrete beam in a parkade for those kind of height restricted environments, a whole series of tanks and controls. And so this is what we're working with and bringing to projects along with our partners. We make it all, we assemble it all here in our fab shop. This is one of a couple of fab shops here in the Tumwater campus. And as we start assembling it, this is what a skid looks like. We saw kind of what droplets look like. And we do, we have all of that redundancy backup. We have isolation valves, and these are 3-way valves so that we can shut off we can leave a system fully operating, valve off an individual heat pump, lock it out, depower it, and then open up some garden hose ports and then do a back flush while the rest of the system's still running. Stop the back flush, open everything back up, let it run again. If we need to pull a heat pump and service it or change it completely, valve it off and decouple it, depower it, and everything's ready to go. Not watching on time, so I'll kind of keep moving here a little bit. Now we get into our management system. So we developed something called the Domestic Hot Water Manager, and it's tailor-made for our systems and domestic hot water systems. They're embedded in every plant. Every plant comes with an LTE SIM card and 4 temperature probes for the tank, a CTA 2045 skybox, this is for load shifting, and installed metering for ambient air temperature, incoming water temperature, and then the final 2 check boxes, I think, are just about check boxes, which means our systems can produce a full system COP and like a full monitoring system. We can talk specifically about that as we need to, but essentially all that equipment's in the panel, be it a skid or a droplet, and ready to go. And we can see it from our engineering desk 24/7, which means if there's alarms or error codes, we can receive them and we can notify. If the system's operating out of range, we can set up some boundary conditions, we can see those or notify. When there's annual service needed, it can report that and we can report it. It's moving away from the day where you have a water heater kind of in the mechanical room of the building and nobody knows really what's going on, especially in buildings that don't have BMS or full management systems. They just have someone that might know a little bit about how the plant works and looks at it every once in a while. We're kind of moving to fully connected plants where we can really support them. And now we move to kind of why we put 4 thermistors in each tank is we're developing smart tanks because really as we look at it, once we understand the condition of the tank from top to bottom, we know how much hot water is in it. Essentially, remember that little bottom kind of blue splash of cold water. Well, as we use up hot water, that blue, we're taking hot water out of the tank and it's replaced with cold water until the heat pumps turn on and lift that cold water to hot. But before that, the cold water level rises up and it can rise up all the way to the top of the tanks. So our thermistors are placed in a position where we can see that thermocline rise up and down, and then we know what status of the tank is. So we're looking at it really like a battery because at the end of the day, all these things use electricity that the building pays for or somebody pays for. And so we're really designing a system to do some energy management rather than just lifting cold water to hot. So because systems will often use multiple tanks, we've created this tank arrangement so that the concept is based on the top layer, single tank, and it's got a thermistor probe at 20%, 40%, 60%, 80%. Those are kind of the fixed place. And our control system knows that thermistor A and thermistor B and thermistor C are in a particular, and thermistor D are in a particular point and represent either 20%, 40%, etc. And if we stage that across multiple tanks, then really all we're doing is rearranging what ports, because we can still put the 20% thermistor into a position that represents 20% of the total storage volume of a 2-tank system or a 3-tank system. It's just a different probe location, right? So once the tanks are set and the equipment's installed, we're just putting the probes in the right port to match the map, and then we can run these load shift plans, which are essentially on the right-hand side. That blue arrow going up and down is that stratified layer of cold water going up and down. And it's passing by those thermistors. And, depending on what utility you're in and what market you're in, electricity costs a different amount during some periods of the day and other periods of the day. Utilities offer a load shed to try to kind of get equipment, to manage the duct curve and use less electricity during the peak events. Well, water heating, because we have storage, is a really good piece of equipment to manage that with. And so there are utility programs that'll manage that. But then we also built our own program that comes with every system. Here's the core of what we're trying to accomplish just by understanding the tank condition, the time of day, and those 2 increments, and really kind of what control system we want to operate. So the gray period in California is 4 to 9 p.m. peak pricing. I'm in San Diego. Peak rate is 84 cents a kilowatt hour during the peak period. Off peak period, it's much, much, much lower. So really, I don't want to buy any peak rate electrons because they're really expensive. I have storage. How much storage I have is not so much an issue. It's always an issue, but I've always got extra storage because whenever we size systems, we're sizing them to the worst day. So even if I don't add extra storage for load shifting, I've got some storage I can always manage. And essentially what we're going to do is we're going to try and not run our heat pumps during this period. And that red line indicates, maybe how it would operate, especially if we didn't have a lot of storage to do any shift with it. And so really the way we're going to accomplish that is we're going to understand the condition of the tanks, and we're going to run a load up sequence and understand how much energy, how much room the tanks will take of additional energy. And so the system will wake up at 1 in the afternoon and say, hey, it's 1 and 4 p.m. is coming and electricity is expensive at 4. So let's look at the tank and run the heat pumps until we fill that tank, and let's run enough heat pumps to make sure the tank's full before that 4 p.m. period starts. So we do that. And that is called our peak rate optimizing program. And so it's a particular selection in our system. And so essentially the goal, what we're trying to do is develop the tank storage to full capacity before we enter that peak rate period, and delay the consumption of electricity at the higher rate for as long as possible, which we can do because we've got so many sensors in the tank that we can really understand the condition of the tank. We can set boundary conditions saying, you know, for one building, a safe edge might be a little more riskier, or a little less margin. In another building, because of anyone's decision, we can say, well, we want to be in a low risk, so even the electricity costs more, bring it on sooner, because I always need to make sure that I've got this extra capacity because of whatever reasons going on in the building. But that's what we can do. So here's actual cases. I'm going to let Steve also kind of step in and say a few words on this. And this is Steve, if I can let you kind of talk about, I think this is Mary Morse.
Yeah, Mary Morse, which was a residence hall in Oakland at what was Mills College and is now is the Northeastern University West Campus. I mean, the case of this is that, you know, with the full skid, you're trying to overcome some of the challenges of knowledge with the contractors. With our agency, we kind of embraced the contractors. We spend a lot of time going over what goes into fill fabricating the majority of the tank configuration, and just focusing on integrating that with the heat pump array. And you know, so local contractors, union contractors, they like that they're going to do the plumbing themselves. It's what they want to do. They don't really like factories building their piping systems. So we built schematics. They're really sharp schematics. We also use the same schematics based on what we're learning in the field to go back to the engineers and show what works. And so this is a layout that was for a 150 unit residence hall there. And you know, it had a lot of preservation concerns, things like that. But we found space, kind of a low ceiling, 7.5 foot space where the water drop tanks didn't work, but we also rep Niles tanks, and we found tanks and could customize them to fit into that small space and get through a doorway that couldn't be taken down because it was a preservation doorway. A lot of the equipment that's in the water drop skids, we represent locally, so we can support a field build with the Calliope Legion mixing valve. That's us, the Magna 3, Grundfos Magna 3, that they use that in the skids, and we represent Grundfos in that area. And so we can support these field builds around all the equipment as well. And then, you know, the nice thing about these arrays, you can put them anywhere. This is sitting right outside the dormitory windows. You said 37 decibels on
Yeah,
these. I mean,
37 dB.
you don't hear them. So
Yeah.
placement for the array was easy. Any place you can find the footprint, it doesn't only needs a little bit of clearance and location relative to windows and things like that. Not a concern. And so this is what we're seeing quite a bit of. We're doing a lot of retrofit because of limitations with space, the inability to just put a full skid on a roof and have it structurally be supported by the building, and just, you know, logistically trying to work out and figure out the best way to make things work. So we are being effective at retrofit and not just new construction where everything's kind of predetermined as how a system's going to go in. We can make a lot of this equipment get in and work. And then you know, Albert's monitoring these systems, so we're learning things on sizing, how to better optimize sizing relative to what we're seeing. So we're gaining knowledge and improving on these installations, and they're effective. We're not seeing issues of lack of hot water, and so different schematics. You could just kind of go through. So this is just one of many that we're laying out there, and we're getting better at putting these schematics together. We're not engineers, but we definitely can create the references for both the fields, for the installation, as well as for the engineers to help kind of work out how they're gonna best put together their plans and incorporate them into their drawings to lay out a system. Okay, I think that's just another representation. We've got numbers of these out there right now on different projects.
Yeah, so we're coming up about one. So I
Yeah.
want to be respectful of everyone's time. Happy to always, I do nothing but talk about commercial water heating all day long, and I'm always happy to do it. So any questions, comments, please fire them out. Lots of information on our website, and we have lots of delivery methods. Mostly, we really like to be involved with our partners in the development of the system. So if we can help out, and Steve can connect us up and we do a sizing and look at a project, always good. So yeah, thank you.
And Albert, you're okay with sharing the deck?
I am.
Anyone who needs it, okay, for reference?
Yeah.
Okay. All right. Well, thank you everyone for attending. I don't think there's any questions or anything. This was all very straightforward. So if you need any assistance, let us know.
Great. Thank you.
All right, Albert. Thank you.
All right. Cheers.
Bye.